Aloha! We have seen all sorts of types of functions, different families of functions. We've looked at polynomial functions and rational functions and exponential functions and trigonometric functions and inverse trig functions and logarithmic functions. And there is a family of functions that you may not have seen before, but I want to talk about it now. These are called the hyperbolic functions. I'm going to give you the formulas for these, the definitions for these functions, and we're going to talk about why they are named hyperbolic functions, where they come up in the real world, identities, and all sorts of things like that. Some instructors include this in a calculus class. Some instructors don't include it. Some instructors talk about it but don't really test on it. It's more of an optional sort of a thing. So depending on who your instructor is, you might have a different situation. You might not even see this in some classes. But let's start, as I said, by looking at the definition of the hyperbolic functions. Boop. Here they are. And you will notice something a little bit familiar. There are 6 of these hyperbolic functions, similarly to how there are 6 trigonometric functions, and they almost look the same. You can see sine and cosine and tangent, kind of. So what these are these are hyperbolic sine, and we put an H at the end of sin, sine, so hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, and hyperbolic cosecant. We write these like we usually would, but with the letter H at the end of the 3 letters. The way that we pronounce these is different depending on where you learned these. When I learned hyperbolic sine, hyperbolic cosine, and hyperbolic tangent, I was told that they were pronounced cinch, cosh, and tanch, which cosh makes sense. Cinch doesn't because there's no C before the H. I've heard that in some countries they pronounce this as shine because there's an H and it's a sign, so shine. I really don't know. There doesn't really seem to be a convention. We can always call them hyperbolic sine, hyperbolic cosine, hyperbolic tangent, but usually if we're dealing with a function and we've got a bunch of these inside of the function, in a pinch, we can refer to this as cinch and cosh and tanch. Just use context and see how things feel as you get used to them. But another thing that is interesting is that we have formulas for hyperbolic sine and cosine, but then if you look at the other 4 hyperbolic functions, these are defined very similarly to how they were with trigonometric functions. Hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Hyperbolic cotangent is the reciprocal of that. And then hyperbolic secant is the reciprocal of hyperbolic cosine. Hyperbolic cosecant, that's a lot of syllables, is the reciprocal of hyperbolic sine. So really, the relationships between these, the very basic relationships, the way that they're defined is the same, except hyperbolic sine and hyperbolic cosine are defined, they're given by these formulas that have exponential functions in them. So for hyperbolic sine, we have e to the x minus e to the negative x over 2. And for hyperbolic cosine, we have e to the x plus e to the negative x over 2. Now, you might be wondering why we give these functions names that are similar to trigonometric functions, but instead involve hyperbolic, the word hyperbolic. And the reason is that they are actually similar, but where the trigonometric functions are often defined off of the unit circle, we can define the hyperbolic functions based off of the standard parabola. Let me just do very quick sketches of each of these for you. All right, here we go. These are very rough sketches. They're not nice at all. We could do much nicer ones with computers, or if I wasn't using a stylus on an iPad that slips very easily. But if we look at the left-hand side here we have the circle x squared plus y squared equals 1. And if we look at any point on that circle, its coordinates can come from cosine of t comma sine of t. As we change the angle t, then this point, given by cosine of t sine of t, moves around the unit circle. And then similarly, we have what we call the standard parabola, x squared minus y squared equals 1. And if we look at a point here on the right-hand side of it, these points can be parametrized by the functions hyperbolic cosine of t and hyperbolic sine of t. And I'm realizing I forgot to put the t there because I was running out of room. There we go. Cosh t and sinh t. So these functions are geometrically related to a hyperbola, similarly to how the trigonometric functions were geometrically related to a circle. Now, why are we talking about these, and why haven't we spoken about them earlier? Well, we haven't spoken about them earlier because, honestly, you spend enough time learning about different types of functions that inserting another type of function is going to take more brain power. But the reason that we talk about them now is because they do come up in a variety of places, particularly in engineering. And many of the students who take calculus are going to end up becoming engineers or working in different science fields, different STEM fields. And so this is the point where we've got a group of students that is likely at some point to see these functions. So this is the moment to start talking about them. So I want to give you a few examples to finish off this video, and then in the next video I want to show you some of the hyperbolic identities that are going to look similar to trigonometric identities. But let's start by looking at some examples of where we might encounter these in the real world. So one place we might see something that is modeled off of a hyperbolic function is if you look between two towers and the power lines that run between them. This is an awful drawing, but I hope you can be amused by it and not upset that I'm going to do some awful drawings today. But the shape of the way that a power line hangs between two towers is given by a hyperbolic cosine curve. We would have the shape represented by some function where we've got c plus a times hyperbolic cosine of x over a for some values of a and c. I'm not an engineer. I haven't really studied that, so I couldn't tell you exactly where c and a come from. I think c is probably the height of the tower. I'm not sure if a is the distance between them or not, but if you're really interested in this, you could look this up more in depth. But I want to just show you a variety of examples. So let's look at another example. If we look at idealized ocean waves, now, not all ocean waves are going to be exactly the same. And of course, there's so many things that affect the exact ripple of each wave. But if we were to look at kind of the ideal version of ocean waves, and these would be much nicer than the ones I've drawn, of course, but idealized ocean waves do have a shape that is related to hyperbolic functions. We can also find hyperbolic functions if we look at certain maps. We know that there are different projections used to show the maps of Earth, because Earth is more or less spherical, but the way we display maps is flat. And so there are different projections that work in different ways. And in particular, the Mercator projection uses hyperbolic cosine in some of its calculations. Also, you might recognize this structure. It is the St. Louis Gateway Arch. And this was also designed using a hyperbolic cosine function. And the last example that I'm aware of is soap bubbles. In particular, when we have a soap bubble that's stretched between two circular objects, this shape is related to one of the hyperbolic functions. So it's a type of function that appears in a lot of different places in the real world. But because we learn so many types of functions in all of the algebra classes, adding another type of function too early might just be a little bit too much for some of the students who aren't moving on to STEM. But those of you who are in calculus and probably going to be in STEM fields and STEM majors should be exposed to it, hence this discussion.